Here's another question from a released free response test, asking me to talk about distance traveled given velocity. So this idea, you could almost expect it to see it in the free response section. So I have another particle is moving along the x-axis, and I have the velocity function. I've been asked to find all times t at which the particle changes direction. So that's a chapter 3 question. We know the particle changes direction whenever velocity changes sign. So I'm going to start, I put this in here because we're going to need it for part D, but it's not really an integration, like a second semester kind of question. So I'm going to have to notice here, this is a not calculator problem. So I'm going to need to solve is the velocity needs to change sign. That means the velocity needs to equal 0. -1 plus e to the -1. Oops. That's a 1 minus t. Cool. So watch this. I'm going to add 1 to both sides. So I'll have 1. Whoops. 1 equals e to the 1 minus t. I need to get that variable down out of the exponent, so I'm going to take the natural log of both sides. I made it look like that was a base on an exponent, but really I'm natural logging both sides. The natural log of 1 is 0. So 0 equals natural log and eing cancel each other out, 1 minus t. So I get the solution t equals 1. T equals 1. I can make a sign chart for velocity, v of t, and remember this is good for all times t is greater than 0. The only critical point, well, the only solution of velocity equals 0 was when time equaled 1. And I can ask myself, to the left of 1, what if I used values smaller than 1 as t. So let's say I used 1/2. So it's 1 minus 1/2. I'd have e to the 1/2. I'd have the square root of e minus 1, which is positive. And if I use a number bigger than 1, let's say I had 5, I'd have e to the 1 minus 5, e to the -4. So 1 over e to the 4th plus a -1 is going to be negative. So my velocity does in fact change sign at t equals 1, and that's how I would write it up. So I wrote the particle changes direction at time t equals 1 because the velocity changes sign at that time. All right, now I need total distance traveled by the particle over this interval. Remember, total distance traveled, I'd want to integrate the absolute value of velocity, which is super easy to do in the calculator section, but on the non-calculator section, I'm going to have to split this up on my own. So I know the velocity is going to be positive from 0 to 1 and negative after 1. So I'm going to integrate from 0 to 1, my positive velocity, get that distance traveled. I'm going to integrate from 1 to 3. The result is going to be negative. I'm going to take that absolute value of my result. I'm going to add those two positive values together and get my total distance traveled. So I'll just walk you through this. This is what I said. I'm going to integrate from 0 to 3, the absolute value of v of t. I could do that with one calculator line if this were the calculator section. But in the non-calculator section, I'm going to have to split it up. I already figured out, ooh, I see a typo. I already figured out that velocity is positive from 0 to 1 and negative from 1 to whatever, infinity. I only need to go up to 3. And I see here, looking at this, that we're going to fix this typo. That should be the integral from 0 to 1, and then here the integral from 1 to 3. That's 1 to 3. And that second integral, I'm going to need the absolute value. That's going to be the same as taking the integral of velocity and then taking the absolute value of the result. Let's see if this works. Okay, so I did this separate. I hope this is helpful. I'm going to need an antiderivative for velocity. So I did this. I wrote just separately, I found the antiderivative so that later I could bring it up here and evaluate that antiderivative over those two different intervals. So here the antiderivative of 1 minus e to the 1 minus t dt. I broke up at the subtraction sign here, because I need a u substitution for the e to the 1 minus t part, but I don't need a u substitution to integrate negative 1. So the antiderivative of negative 1 is negative t, and I made a u substitution. U equals 1 minus t, du is negative dt, that's a negative sign, so negative du equals dt. That's how I end up with the antiderivative of the opposite of e to the u du. This is a general antiderivative for my velocity function. I'm going to take that antiderivative and use it when I evaluate my two definite integrals from up above. Let's see if I can figure out how to get that back. Okay, so good. Here I have the ones. Remember, we fixed this one. That lower limit should be 1. So my antiderivative, which I just figured out sort of separately, negative t minus e to the 1 minus t, I'm going to evaluate from 0 to 1. I'm going to evaluate it again from 1 to 3, but the result, when I integrate from 1 to 3, I'm going to take the absolute value. All right, so you can just see that. Remember that e to the 0 is 1. Anything raised to the 0 power is 1. And then e to the 1 is just e. That second part needs absolute value bars. If there's any consolation, they haven't asked for you to split up an integral to find total distance traveled by hand. Several years. But we want to be able to know how to do it. All right, so you can see I'm going to erase that little guy, that little mark out of the way. You can see my result, negative 1 plus e to the negative 2.